we will be presenting our final class project for detecting cancer in gigapixel pathology images. We will first get started on our presentation with the background information. Currently, metastasis detection is being performed by pathologists who slice up biopsy or a volume of tissue and put them on the slide, which are then observed under a microscope to determine whether tissues are cancerous. This process is labor-intensive and very error-prone. Also, there aren't enough experts and they don't have enough time to spend analyzing each tissue. With Chameleon 17 dataset from University of Netherlands, our goal is to build a tool that can assist, not replace, pathologists with detecting tumor by leveraging a convolutional neural network architecture. Chameleon dataset contains a set of gigapixel images of a pair of tumor mask and tissue that have multiple zoom levels embedded in a single slide as shown below. Inspired by pathologists zooming in and out to capture context as well as detail when analyzing slides, we use deep zoom to extract slides at multiple different zoom levels. We'll walk through the code base starting with data extract IPYNB. We mount a Google Drive to access slides, then split tissue images to be used as train, validation, and test. I allocated 15 slides to train, 3 slides to validation, and 3 to test. The directories were initialized such that train validation has zoom levels 1 through 5, and within each zoom level, the images are divided into tumor and no tumor. The zoom levels are such that 1 is most zoomed in and 5 is most zoomed out. The test folder divides images into zoom levels and has no labels. In the pre-processing step, we partition the image into 299 to 99 slices and read each slices. We first extracted the dimension of entire slice, which is represented by xdim by ydim, and so that I can enumerate how many 299 to 99 slices I can partition the slide into, which is xnum by ynum. I retrieve each slice from the tissue slide and tumor mask by using read slice and defining x and y. If the slice has at least 30% non-gray region or has 30% tissue, then I extract. If the corresponding tumor slice has a pixel value which indicates there is a tumor in the slice, then the slice will be labeled as tumor. Otherwise, the slice will be labeled marked no tumor. We extracted slices similarly for the test data, but without label. Clearly, there are much more data for no tumor compared to tumor. Thus, we tried 2 techniques. First, we weighted the loss function for tumor and no tumor class using sklearn's compute class weight, assigning class weights for tumor and passing the weights in as parameters when training the model. We also downsampled no tumor data to balance the dataset. We ended up using artificially balancing the data because it produced better results. Now I will explain the model architecture. First, we use transfer learning with Inception v3. Here in the model's Python notebook, you can see that we use Inception v3 as convolution based with ImageNet weights, and we compile model on the zoom level 2, and this is the accuracy and loss plots we got, and we also plotted confusion matrix, and the evaluation metrics will be explained later. In addition, we also made our custom model for binary image classification using CNN, and so we have convolutional and max pooling layers alternating, and we also added dropouts, and we compiled on zoom level 2 as well, and we get accuracy and loss plots as following, and we also did it on different multiple zoom levels such as zoom level 4, and we got accuracy loss plots as following.
To generate the heat map, we used a sliding window of size 299 by 299 pixels over the slides. The step size at which the window was sliding over the slide can be easily controlled. For each window, we used our model to generate a prediction and add the prediction to the heat map. This is an example of a heat map generated for a slide with step size 150. By adding the prediction value to each window on the heat map, we get a gradient of colors, where the color red represents the areas of the heat map with the highest probability of containing a tumor as predicted by our model. This code can be found in the heat map notebook on our GitHub repository. Our heat map function takes the slide image, the model used to generate predictions, the desired width and height of the final heat map, and stride, or step size of the sliding window. So for lower stride values, we expect a finer, more resolved heat map, but this also takes a longer time to generate. This part of the code shows our sliding window of size image dim, which we have set at 299, taking the step size specified by the stride parameter. Finally, we add the model's prediction value to our heat map, which is downsized according to the width and height parameters. This cell is also in the heat map notebook, used to generate the heat map for tumor slide 91. We specify a width and height of 1000 pixels and a stride value of 150. We obtain the heat map by calling the heat map function with the model trained on patches of zoom level 2 and overlay the heat map over the original slide, which also has been downsized to 1000 by 1000 pixels.
Now I will walk through the code demo for generating heat map on the test data. So basically we used tumor 94, which is allocated in the test, and this is the expected tissue and the tumor mask, and this is at zoom level 3, so we loaded model zoom level 3 for custom, and we predicted this outcome. As you can see, the location of tumor predicted is not quite accurate. This could be due to multiple reasons, such as lacking data in zoom level 3 because we undersampled a lot, and also since we use custom model, it was difficult to find the right hyperparameters for the model, and the model was quite deep and had a lot of neurons per layer.
Next, we wanted to try to combine two different zoom levels as the paper did to see if that would improve the accuracy of our model. This required us to generate new data from the existing slides. We decided to use patches from slides at zoom level 3 and 4, and this is how we generated the data. For each patch at zoom level 3, we found the coordinates x and y that it was centered on. Then we find the label for that patch, and then generated another patch centered at the same x and y coordinate at zoom level 4. We do this for all window patches of zoom level 3. This is a snippet of some of the patches that we generated. The grid of 4 patches on the left correspond to the patches at zoom level 3 and the right at 4. So 2 patches that belong to the same pair have the same name. So tumor 0161092 for zoom level 3 and 4 are centered at the same point on the slides, and tumor 0161093 for level 3 and 4 are centered on the same point on the slides, etc. The red squares correspond to roughly where the patches at the corresponding zoom level 3 are located on the patches at zoom level 4. One thing to note is how we created patches beyond the boundaries of the slide. We did this by padding with zeros. Above is 2 patches generated at zoom level 0 and 7 centered right at the bottom right hand corner of a slide. Where the patches extend beyond the slide, the image is black, representing the padding. Moving on to the multi-zoom model, we decided to use our own smaller custom models for each submodel, as we found that our own custom model provided accuracies for true positives as compared to using a pre-trained model. Also, using smaller models to save us training time. The 2 submodels for each zoom level was constructed in the same way. Each submodel took an image patches of size 299 by 299 as input, followed by a convolution layer and a max pooling layer with outputs 32, 64, and then 128, topped off with a flattened layer. This flattened layer would then feed into the concatenate layer, which combines the outputs from both models. The final densely connected layer atop both models outputs the 64 weights, and finally an output logit. Next, we had to combine both inputs. We had to create our own generator that outputs images from both generators as pairs with their shared label. The function generate_generator_multiple was taken from an example online, which takes in 2 directories corresponding to both images. Note that both directories have the same number of images so that this works. Then it outputs images in pairs followed by their label. We use this for both the training and validation set so that our multi-input model works. After running our model over 20 epochs, this is the results we managed to get. Our validation accuracy hovers around 80 to 85%, and our loss around 0.45. Similar to the paper, we found small or negligible improvements in our model when combining multiple zoom levels. However, this might also be due to the fact that our zoom levels were higher, and we also used smaller submodels. The sensitivity, we believe, is our most important metric, as this basically says that given a patient has tumor, our model will say that a patient's slides contain tumor patches with high probability. This is essential in quickly alerting patients that they should seek quick treatment. Specificity is another metric, which is the percentage of correctly predicted non-tumor slides in the pool of slides that have classified no tumor. We will also consider precision. High precision says that most of the patients who receive a positive prediction have tumor. This helps the hospital and patients save costs by reducing the need for unnecessary treatment and tests, as only the patients who need treatment receive it. We also consider negative predictive value, which is the percentage of true negative values in the pool of predicted negative values. This is an important metric, though we believe may not be as crucial as sensitivity. High predictive value essentially increases the reliability of the model, by saying that if the model classifies a patient's slides as having no tumor, the patient very likely does not have tumor. The F1 score is a better indicator of accuracy than vanilla accuracy in our problem, since in our problem the severity of having false negatives is higher than that of false positives. A false negative will send a sick patient home, whereas a false positive simply requires a healthy patient to be further verified by a specialist. Therefore, we must pay closer attention to this metric. The last metric we will compute is the Matthews correlation coefficient, which is best used for imbalanced data sets. It penalizes wrong classifications in both classes according to different weights. The metric ranges from -1 to 1, where 0 represents no better than random classification, 1 represents perfect classification, and -1 represents total disagreement. We trained 3 models using our dataset. Here are the results for the 3 models. The viewer can pause at a specific slide for details. I will compare the metric for the 3 models side by side. These are the metrics for all our 3 models side by side. Even at first glance, we can tell our 3 models are highly inaccurate and should not be used in practice to classify patient information. Regardless, we will examine each metric in closer detail. As we had mentioned earlier, sensitivity was our key metric, and this suggests that our inception model at zoom level 2 was the most accurate at 41.5%. However, this is still highly inaccurate and should not be used by any means. While specificity for our custom CNN at zoom level 2 is high, which means that it classifies 70% of non-tumor slides correctly, this is outweighed by its low sensitivity metric. Therefore, this model should also not be used. All 3 models have precision at about 33%, which means that all positive tumor patches predicted, 33% of them do not actually contain tumor. In the same vein, negative prediction value falls around 61%, which means that all of the negative patches predicted, 61% of them actually do not contain tumor. This is definitely a cause for concern. Due to undersampling, we ensured that there was the same number of tumor and non-tumor patches. We suspect that our model may simply be a close to random model, which outputs its prediction at random, as can be shown by the close to 50% accuracy and close to 0 MCC metric. In fact, the metrics for all 3 models are negative, saying that our models are mostly disagreeable with the correct labels. The F1 score for our 3 models are low, with the highest for the inception model at 38.7%. This is also an indicator for why none of our models should be used. We realized that our model is highly inaccurate, and despite hyperparameter tuning, we found that we could not significantly improve the accuracy of our model. We therefore want to discuss possible sources of error for our model so that we can address these possible sources in future work. One possible source of error could be due to our tissue threshold of being 30% too small. The reason why we chose such a small threshold was to increase our training data size. However, this also led to our training set perhaps containing too many patches with too little tissue information, which might have interfered with the training process. Another could be that our data set was just too small to train on due to undersampling, where we had to throw out many non-tumor patches. We were left with about 2,000 patches in each class for the zoom level at 2, for example. One last possible grave source of error might be that our data set was simply pre-processed and labeled wrongly, therefore arising to the model learning wrong labels. However, we do believe this is unlikely after having overviewed our code base. Going on to future works, we believe the accuracy of our model could be increased by using more slides at the lowest zoom level 0. However, this took us more than 15 hours to generate the data, and we did not think it would be time efficient for us to use the data at this zoom level. Next, we played with the hyperparameters and found the current configuration gave us the most reliable result, but believed that giving more scrutiny to especially sample weighting could improve our accuracy specifically for true positives. Also, our multi-zoom approach only used 2 zoom levels due to time constraints, but combining more than 2 zoom levels could also improve the accuracy of our model, though the original paper said that this only provided marginal improvements. Lastly, we did not try an alternative pre-trained model, but stuck to the model that the paper deemed the most appropriate for our goal. However, it would have been ideal to experiment with other models such as MobileNet and VGG just to compare the results.